Oh, hello. So today we want to look at finding limits. So I guess the first question, obviously is what is a limit? And for most cases, it's a pretty simple idea. Okay, so let me just draw kind of a graph. Okay, so we have this kind of parabolic looking function, and maybe it goes through the point 2, 1, and then zips back up here. Okay, so the question is really what happens to the f of x values as the x value approaches something. So let's say as x maybe goes to 2 on the x-axis, then f of x goes where? So what is happening to the y values as the x values go to 2? And you could kind of analyze it in a numerical way, which we'll talk about here in a second. But right now we're kind of thinking in terms of a graphical method. So as x goes to 2 from the left, so you imagine there's maybe a dot here. The corresponding y value would be somewhere above 2. And then as we get closer to 2, the corresponding y values are decreasing. And then as we approach 2, the corresponding y values are getting closer and closer to the y value 1, right? So we would say, at least from the left, it seems that f of x is going to 2. We also have to consider then from the other direction. So over here, the y values are initially kind of like maybe up at 3, and then they decrease, and as we get closer and closer to 2, the y values are getting closer and closer to the y value 1, right? So over here on the y-axis, they're getting close to this point 1. So for the most part, it's just it's pretty obvious as to what is going on, is maybe my point. So another example, maybe we have the line y equals x, right? So that's the diagonal. And we want to know what happens to the y values as x gets closer to 1. So as x approaches 1, f of x goes to what? So as we come in this direction, the y values are increasing, and as we get closer and closer to 1, it looks like f of x is getting closer and closer to 1 as well. And also from the other direction, it's just in the other direction the y values are decreasing. Okay, but they seem to both go in the same place. Okay. The problem is when you have maybe a piecewise defined function, or if you have some crazy oscillating function. So here in this picture in WebAssign, you see that the point that we're approaching is kind of defined to be not somewhere on the graph, right? It's some other point. With limits, though, we don't really care what happens at the point. It's all about approach. So we're just talking about getting really, really, really super close. So if you're looking at this picture, as the x values approach 1, the y values seem to be approaching the number 3. Okay, f of 1 is actually equal to 1, and you can see that as it's defined in the function. If f of x is equal to 1, then if x is equal to 1, then f of x is 1. Okay, so there's also some notational issues that we'll want to deal with. So, for example, as x goes to 2, f of x goes to 1. We'll write that with this symbol, the limit as x goes to 2 of f of x equals 1. Okay. The second picture, we would say the limit as x goes to 1 of this other function, maybe we call it g of x. In this case, it's also equal to 1. Okay, so you see that symbol in your homework there. The limit of f of x as x goes to 1. In this case is 3. I mean, it's defined to be 1, but again, with limits, we only care about what's happening super duper 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 close to the x value. We don't care what happens exactly at the x value. Problem 6 here, we see approach from two different sides are different. So as I approach from the left side, the y value is always apparently negative 1. Okay, so I approach from the right side, the y value is always 1. So as x approaches, looks like 4 in this case, from the left, the f of x is approaching, well, it's always negative 1, but approaching, and it's always negative 1. From the right, it's always positive 1. And that's an issue. So we'll talk about how limits fail in this section. And one of the ways it could fail is if you have different left and right hand approaches. Number 7 is another one of these ways a limit can fail. So maybe you wonder what the limit would be here, and we'll look at it on Desmos here in a minute. This oscillating phenomena will cause a limit to fail. Another way it could fail is from unbounded behavior. So if you look at pi over 2 and we're coming in from the left, the graph is just getting larger and larger. It's going off to positive infinity, right? So it's not like we put an answer on that. It's just the numbers are always getting bigger and bigger the closer we get to pi over 2. So it's another way the limit can fail to exist. Okay, so let's look at this problem here. What is this, problem 9? And figure out the answers here. So they give us a nice graph, f of 1. So what is literally f of 1? It looks like f of 1 is defined to be 5. Okay, so the y value at f of 1, where the closed dot is 5. And then, so what's the limit as x goes to 1 of f of x? So coming in from the left, the curve is dipping down and then going back up, and it looks like it's getting really, really close to 7. Coming in from the right, it's coming down, it's getting really, really close to 1 on the y side. So we would say that limit does not exist because it has two different sides, two different approaches. Okay, limit as x goes to 1 of f of x. So as f of 6 then. F of 6 is not defined. There's just an open dot there. There's no closed dots floating around. So we would say it does not exist. But the limit of f of x as x approaches 6 does exist, right? It's getting really, really close to, it looks like 5, right? Okay, so maybe we can even look at this guy. Wow, this one looks like a nightmare. So it's x squared when x is less than 2, so it's a parabola. Then it's 8 minus 2x, so I think it's this, and then 6 up here when it's greater than or equal to 4. So yeah, it's this graph here. So the limit, what's the limit? Identify the values of c for which the following limit exists. So this has a limit everywhere, it seems, except this place where you're coming in on two different sides. Okay, so approaching from the left, it goes to 0. Approaching from the right, it goes to 6. Okay, so graphically, you're kind of just reading off what happens to the y values as the x values get really, really close to something. Okay, so let me get back to my notes then and take a look at just doing some numerical type analysis to one of these graphs, right? So this example, we want to sketch it and then figure out what's happening as we approach kind of this point, which is not defined. So f of x is x minus 4 all over x squared minus 3x minus 4. And we want to know the limit of this thing, this f of x thing, as x approaches 4. Okay, what's happening to the y values as the x values approach 4? Well, one way to approach this, and usually the easiest way to approach this, is to literally just plug 4 into the equation. Okay, so if you did that, what would happen? Well, you would get x minus 4, so you put in 4 there. It's 4 minus 4 is 0. And then in the denominator, if you put in 4, you get 16 minus 12 minus 4, which is 0 as well. We don't know what 0 over 0 is. That's kind of kind of a mystery at this point. So what we can do instead is a numerical analysis, okay, and just kind of guess, right? Because we don't really care what happens exactly at 4. We just want to know what happens as we approach 4. So what I do is make a table and consider the values as we approach 4 from the left and the right. So I'm going to put 4 here in the middle. And then on the left, I'm going to go something like 4.1. Oh, whoops, wrong direction, right? 3.9 is what I need. Okay, so I'm going to put 3.9, and then 3.99, and then 3.999. So getting really, really super duper close to 4. On the other side, you're thinking like 4.1, 4.01, and then 4.001. And this is where having like a TI calculator really helps, because you could just put this function into your y equals menu and then look at the table, okay, that's associated with that. Okay, but anyways, I went ahead and plopped them all in earlier, and I'm getting 0.204 and then 0.2004. And I encourage you to pause the video and just fill out the chart yourself. There's nothing better than actually doing something to learn it, right? And then in the middle here, I don't know. And then on the other side, it's going 0.196, 0.1996, and then 0.19996. So what does it look like it's getting really close to? Well, I think, and I'm not sure, I think this is only a guess that it's getting close to 0.2. In other words, 2/10, which is 1/5. Okay. Okay, so my guess, I'm not sure, I'll put it back up here though, my guess is that it's getting really, really close to 1/5. Okay. We can plot this thing just by this sort of clever removal. If you were to factor the denominator, what would you get? Well, you get x minus 4 times x plus 1. And then you can remove the top and the bottom so long as x is not equal to 4, because it's undefined there. At x equals 4, it does not exist. And everywhere except that, it's going to have the behavior of 1 over x plus 1, which we can plot just using kind of a shift, right? A shift of originally 1 over x is the kind of has asymptote at 0. This thing will have an asymptote at -1, and it'll look like this. Okay, except at 4, it's going to be undefined, so we're going to put like a hole there. Okay, so you can see from the graph that as we approach 4 from the left and the right, all you get is basically this y value here from our sort of similar graph of 1 all over x plus 1. So if we put in 4, we should be able to kind of figure out the answer, probably, right? So let's see if it works, right? 1 over 4 plus 1 is 5, and sure enough, yeah, that was what we presumed it was going to be through our numerical analysis. Okay. Okay. So let's look at another one with one of these piecewise functions. These come up if you do a lot of electrical engineering, because they model on and off switches. Okay, so use the graph to find the limit. And here we have the limit as x goes to 2 of f of x. And the f of x is defined piecewise to be 4 minus x if x is not equal to 2, and then 0 when x is actually equal to 2. Okay, so what does that look like? Let's take a look. I'll graph 4 minus x, so its y-intercept is at 4, and then it's going to go down 1 over 1, down 1 over 1. 3, 4, except at 2, where there's going to be an open dot on the line. Okay, so everywhere except 2 it's the graph of the line 4 minus x. And then at 2, it's defined the y value will be 0. So 2, 0, you'll have a closed dot right here. Okay, so we want to find the limit as we approach 2. And again, the limit is not about what exactly happens at 2, it's about the approach to 2. So as we get super duper close to 2 on the x-axis, the y values seem to be just getting really, really close to whatever the line is getting close to, right? So it seems like it's this value right here on the y-axis. So whatever this point is on the line, it should be kind of is going to give us our answer. So if you take 4 minus 2, you would get 2. So it seems like as we get really, really close, our limit is going to be 2. Okay, so you're just kind of tracing out what happens to the y values as the x values approach some number. Okay. So it's instructive to look at when limits fail, and we'll be using limits a lot. So you kind of even almost want to memorize when do limits fail. And if we were in a real class, I'd kind of pound it into your brain. But limits that fail to exist. Okay, so the first case is when you have different left and right hand behavior. Okay, and an example usually comes up when you're dealing with these kind of funny absolute value type functions. So here in this example, we want to figure out what's happening as x goes to 0 of the absolute value of x over x. Okay, so first off, let's investigate. How do I interpret the absolute value of x over x, right? Well, if you remember the definition of the absolute value of x as a piecewise function, maybe let me smoosh that in over here at the top right. It's negative x when x is less than 0, and then positive x when x is greater than or equal to 0. Okay, so I can replace the numerator with negative x when x is less than 0. And of course I could simplify that, right? That's just negative 1. And then I can write the numerator as positive x when, which is equal to 1 when x is greater than 0. I can't go greater than or equal to because it wouldn't be defined at 0. It'd be a 0 over 0. And I have to investigate the limit to see what happens, right? Okay, so the picture, and that's kind of what we're going to look at, right? So there's a graphical analysis. As we come in from the x values from the left, the y value is always going to be negative 1. Okay, so the graph would look like this. So as x goes to 0 from the left, seems like f of x, well, obviously f of x is going to negative 1. It's always negative 1. And then for x greater than 0, it's positive 1, right? So the graph would look like that. So as x goes to 0 from the right, f of x is going to positive 1. So we have different left and right hand limits. So that means this limit at the top left here does not exist. And we would write DNE for does not exist. Okay, so that's the first type of non-existent behavior. The second type is the unbounded behavior. And this is where you have a limit basically going to it just keeps getting higher and higher and higher, or lower and lower and lower. So it's kind of going to positive infinity or negative infinity on us. Okay, so take an example. I think this is the one they have in WebAssign as well. Okay. So the limit as x goes to pi over 2 of tan x. And again, we're going to do a graphical analysis. So tan of x, it looks kind of like a cubic, you know, but it has asymptotes on it. It goes like that, and then it's periodic. Right? This is pi over 2 right here. And then pi, and then 3 pi over 2 is over here. and it's periodic, right? Okay, so what is happening to the y values as we approach pi over 2? So as x goes to pi over 2 from the left, and another way of saying from the left is just put a little negative sign in the exponent. Okay, so as x approaches pi over 2 from the left, f of x seems to just be getting bigger and bigger and bigger. So we're going to call that going to infinity. Okay, as x goes to pi over 2 from the other direction, from the right, f of x is going to the bottom. It's going to negative infinity. The y values are getting smaller and smaller and smaller and smaller, right? So that's considered unbounded behavior. And in particular, it's going in two different directions. So it's unbounded and the left and right hand behavior is different. So we'll say that does not exist. And in general, if it was going to infinity in both directions, so if you had something like this with an asymptote right here, it would still be non-existent. It's just we would say something like the limit of f of x, we'd actually put a name on it, would equal infinity at this asymptote, whatever that is. Maybe it's like 2. Okay, but here it's going in two different directions, so we're just going to say it does not exist at all. Okay. Okay. What else? So the third type of non-existence is the oscillating type. Okay, and we're going to take a close look at this function on Desmos. So the example, the limit of cosine of 1 over x as x goes to 0. First, we're going to do some numerical analysis. Okay, so I'm just going to look at a table of values, and I make up my table so that the x values are going, so I'm going to go from the right, approach from the right, and take a look at x values going to 0. But I'm going to create the x values in kind of a creative way, right? So I'm going to go 1 over pi, and then to make the denominator smaller, to make it closer to 0, I'm going to increase the denominator. 1 over 2 pi, 1 over 3 pi, 1 over 4 pi. And certainly these numbers are getting closer and closer to 0 because I'm increasing the denominator at every step. Okay, what's happening to the y values though, right? When I put these values into the cosine of 1 over x, I get the cosine of 1 over pi. 1 over pi is the same as pi, right? So I get the cosine of pi, and then that will equal -1. Okay? The second one is the cosine of 1 over 2 pi, which is a cosine of 2 pi, which would be +1. And then it's going to start oscillating. It's going to be -1, +1, -1. And it'll keep on doing that forever and ever. As close as you get to 0 as you want, you could still find a place where it's jumping back and forth. Okay, so this oscillating behavior means that this limit does not exist. Okay, let's take a look at Desmos, which is a great place to go for graphing. Okay, if you've not been there, I hope you go there and play around with some of this stuff. Desmos. Okay, so let's get the graphing calculator going. And let's see what this is, right? Why not? Cosine of 1 over x. Okay, so not very informative as it sits, but we can zoom in, right? So let's zoom in, and zoom in, and zoom in, and zoom in, and oh my gosh, this is a nightmare. You know, we've opened Pandora's box, so to speak. Okay, so it's a very unusual function, not something that you're used to, right? Or used to like parabolas and lines and maybe cubics and stuff. But this is some nightmare function. This is crazy. Okay. And it keeps going up and down and up and down. And who knows? Desmos can't even figure it out, right? All right. Okay, so let's get out of there. So anyways, as we approach 0, in that case, the limit does not exist. Okay, back you know, and 100, 200 years ago or 300, I'm not sure about the history of it, but mathematicians really went crazy about formalizing everything and making everything exact. And this is kind of a hard idea to even wrap your brain around in these modern times, right? It's like, well, the x value is getting close. What is the y value? And I'm not even still sure what a limit is, you know? But they've tried to formalize this idea. So the formalization of the limit. And if you kept taking math, you would eventually beat this to death. If you become a math major, this would be the kind of thing that you would be interested in once you got to stuff like advanced calculus and real analysis. But we introduce it here, and we want to do a couple of these types of proofs as well. So how do I formalize this idea of a limit? And it's all about distances, about something getting close and then the corresponding y values getting close, right? So anyways, here we go. All right, I'll just write it out. So let f be a function defined on some open interval containing some number c that we're approaching, and except possibly at c, because we don't really care about what really happens there. Okay, and let L be a real number. And then the statement, LIM, this thing that we've been working with, the limit as x approaches c of the function f of x equaling some number L. What does that mean strictly? It means that for any epsilon greater than 0, so epsilon is a Greek letter. It just represents a small number, like 0.0001 or something. So it just means we're getting super duper close to something, which is what the limit, we're talking about. So it means that for any epsilon greater than 0, there exists delta greater than 0, so another Greek letter that represents a very small number. There exists a delta greater than 0, such that for any x in the open interval, if the distance between x and c is super small, so as we get really, really close to x, or sorry, as we get really, really close to c, then we get really, really close to this number L. So the actual y values get super duper close to L. So if you're not used to thinking of the absolute values as a distance, that's what the absolute value is, right? So remember, if you have something like the absolute value of -3, what does that really represent? That represents the distance between 3 and 0. Right? So on the number line, here's -3, 1, 2, 3, at 0. And what is the distance between those two? Well, the distance is 3. That's why we kind of change the sign if you put something in an absolute value. Okay, so at least on the number line, absolute values indicate distance. So you're used to you just make the negative number a positive number. Well, no, we want to use it for distance, okay? In the plane, you have to use a square root and all that stuff. And you could even rewrite this definition with different kinds of distances instead of absolute values. You could use distance in a plane or distance in space. They can make up arbitrary distances as distance formulas too. So the limit is all about something going in one direction. What happens to the output? What happens to the output as the input gets really, really close to something? And you can imagine different kinds of universes where distances are different, maybe in the quantum universe, I don't know. Okay, so it's a definition. If you kept taking math, you would beat it to death, and you would look at it in all kinds of what they call different metric spaces and stuff like that. Visually, it's the same thing as what we've been talking about above. You know, we're getting really, really close to some C value. Okay, so we're going to basically get really close to it, and the closeness is determined by this delta, right? So we're within delta of the C, so around C minus delta, the C plus delta. And the limit is saying that if you're in that interval, anything in that interval will be within epsilon of L. Okay, so L plus epsilon and then L minus epsilon. And you kind of can make a little picture here. So maybe our graph is kind of going like this, and then doing something, I don't know, and then maybe going out like this. So for any x value that you can imagine in this interval, or for any epsilon really, you can imagine, you can find a delta such that for any x value in this interval, the distance between f of x and L will be within epsilon. So it's a strict definition. It's you know, it's not intuitive by any means, but there it is. Okay, so we want to play around with these delta epsilon proofs a bit. It would be wrong for me to not teach you how to do these. So let's take a look at doing epsilon delta proofs for proving limits. Okay, so we'll take a look at an example first off. Given the limit LIM as x goes to 3 of 2x minus 5, what does this equal? Sometimes you could just literally substitute the 3 in there, so it'd be 6 minus 1. 6 minus 5 is 1. Find a delta such that a delta around 3, so a little interval around the number 3 on the x-axis, such that if we're in that delta, so such that if you pick any x value in this interval, then the y value, the f of x value, will be within epsilon of the number 1, the y value 1. So it's getting really, really close to 1. Okay, so minus 1. And they're going to give you some epsilon value. So they're going to say something like 0.01, and that's our epsilon value. Okay. So the picture, you know, x minus 3, 1, 2, 3, and then 1, 2, 3, and then 1. So we're getting right here. Okay. Crap, that's not the right. Sorry. So it's at 1. It's right here. So negative 3, and then it's kind of like doing this. Okay, so we want to find an interval such that if I take an x inside of this interval, so if I take an x inside there, maybe I should put the interval in a different color, right? If I take an x inside there, it'll be within 0.01 of 1, okay, on the y-axis. So it'll be in this little interval. Okay, and the way you usually go about doing this is kind of a back engineering, okay? And it's a bit weird when you first see it. Okay, it's not so weird though. You kind of always do it with algebra. If it was an equation, it'd be equal. It would be easy. But because it's equal, because it's an inequality, it's difficult. Okay, but let me show you how to do this. Okay, so how am I going to do this? How do I find that delta? Okay. Well, you back engineer it. You're going to start with this thing right here. So start here. And then you kind of go from there to kind of produce this thing. Okay, so let me show you again. I start with the f of x minus 1. So what is my f of x? My f of x is the thing inside the limit. Okay, so it's this thing right here. That is f of x. Okay, okay. So this equals 2x minus 5 minus 1. Okay, and what I hope to do is kind of extract an x minus 3 from this. So 2x minus 5 minus 1 is 2x minus 6. And I'm trying to back engineer an x minus 3. I want the first part of that if-then statement in the middle of the page there. And I could do that by factoring out a 2. And this will generally work, okay? At least in these easy cases. So I have 2 times absolute value of x minus 3. And I want this thing to be less than my epsilon. And right now my epsilon is 0.01. Okay? So I solve for the x minus 3 in this new statement. So I have 2 times the absolute value of x minus 3 is less than 0.01. Just divide both sides by 2. So x minus 3 will be less than 0.01 divided by 2, which is 0.005. Okay? And then that is sort of our answer. That's the delta that we want right here. Okay? And we could show that works. So if we suppose, you have to include this greater than 0 part. If you could show that x minus 3 absolute value, if you suppose this is true, 0.005, then we'll have f of x minus 1, which equals the 2x minus 5 minus 1, which equals the 2 times x minus 6, which equals 2 times the absolute value of x minus 3. That'll be less than 2 times, well, I know absolute value of 3 is less than 0.005. Okay, so I could say that this then is less than 2 times 0.005. And of course, that's equal to what? That's equal to this 0.01, which is what I wanted to do. I wanted to show, ultimately, back here up at the top, this thing. I wanted to find a delta such that if x minus 3 is less than that delta, then f of x minus 1 is less than 0.01. Okay. Okay. Let's actually do a concrete proof then of this sort of method. Let me look on WebAssign real quick to make sure there isn't any other type of limit we need to worry about. Okay, I think we're good. Oh no, there's these other kind where you have a square involved. Okay, so the other kind then I have to show you. Another example then is something like proving the limit as x goes to, let me find one, as x goes to 4 of x squared minus 9. Okay, so if you substitute 4 into x squared, 16 minus 9 is going to be 7, right? Okay, I want to find, this time, a delta such that if x minus the distance between x and 4, so where am I getting the x minus 4? That's from the bottom part of that limit above, right? So the x arrow 4, I just kind of change that into x minus 4. Okay, so I want to find a delta such that if 0 is less than x minus 4 is less than delta, then this f of x, which in our case, f of x, what is f of x, right? It's the x squared minus 9 part, such that f of x, which is x squared minus 9, the distance between that and 7 is less than some epsilon. So they'll give you some random number like 0.001 or something, right? And that's our epsilon. Okay, so again, it's a matter of back engineering, but this problem is a little bit more complicated. Okay, and in order to make it work, we have to do some basic restriction. Okay, in particular, on the x-axis, if you think about how these limits work, okay, and if we could draw a picture really quick. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have this picture of our parabola, at least part of it. I don't know what the vertex is 0, -9. We want to know what happens to the y values as we approach 4, right? It doesn't make that much of a difference if you restrict your x values to be within 1 of 4. Okay, in other words, what we want to do to make this all pan out, and it may seem weird right now, but there is a method to my madness. What we want to do is make sure that first x minus 4 is less than 1. Okay, so it's kind of a preliminary assumption that we're going to use in order to find our delta. Okay, so now the back engineering part, right? So I work with the second half of the if-then statement, this x squared minus 9 minus 7. I notice that this is equal to x squared minus 16, and then I can factor that. Okay, that's x minus 4 times x plus 4. And then the product rule of absolute values says you could break that apart into two absolute values, x minus 4 times the absolute value of x plus 4. And then as we did above, what did we do once we sort of back engineered that x minus 3? We sort of solved, right? So here we want x minus 4 times x plus 4 to be less than 0.001, and then we solve for the x minus 4. So, but there's a problem here, in that we're getting a variable expression. We don't get just a nice delta number. Okay, and that's where this assumption about x minus 4 being less than 1 comes into play. Okay, so we use this inequality in order to figure out how to put a restriction on the x plus 4 part, and then we'll have our epsilon. Okay, so if I expand x minus 4 less than 1, what do I have? X minus 4 less than 1 and then greater than -1. Okay, I want to kind of back engineer this time x plus 4. So if I add 8 to all three sides, what do I get? I get 7 less than x plus 4 less than 9. So here I could say the absolute value of x plus 4 is actually less than 9. And then I could replace the x plus 4 in that circled expression over there. So over here, I could replace the absolute value of x plus 4 with a 9. Okay, and that's going to give me my epsilon. Okay, so I'm going to just sort of rewrite this as 0.001 over 9. Okay, and then that will be the particular delta that I need. Okay, right, so there's one extra little bit, because I made that initial restriction, x minus 4 has to be less than 1, I have to say let this x minus 4 thing be less than this delta that we just found, which is going to be equal to the minimum of 1 and 0.001 over 9. Okay, which is a little weird, but don't overthink it at this point, right? Okay, and then you could check it, right? We note if that is true, then x squared minus 9 minus 7, which equals eventually x minus 4 times absolute value of x plus 4, will be less than, the x plus 4 is less than 9, right? And the x minus 4 is less than 0.001 over 9, and times 9, because x plus 4 is less than 9. I guess at this point we really don't even need this min part. We could just say, sorry, I apologize. We could just say we need that for the general part of the proof. For right now, we could just say 0.001 over 9. And then if we multiply these together, the 9's divide out, and we're just left with the 0.001, which is what we were trying to show. Okay. So if this x minus 4 is less than this delta that we just made, then the x squared minus 9 minus 7 will be less than 0.001. Okay, so these proofs are pretty crazy if you've never seen them before, but they're not really that bad. And what they are a particular class of proof called universal existential proofs. Okay, and you could take a class in proofs. Usually in classes like discrete math, they'll worry about proofs and doing proofs, but you probably need like a class in modern math or some sort of proof class, like Ohio State. They probably have a class just doing proofs and mathematical logic and that sort of stuff. But anyways, universal existential proofs, and what we've been doing is kind of weird, and I've been talking about it. Let me just give you a general version. We want to prove something like prove for all x there exists a y such that x plus y equals 7. So this is the same type of thing that we're trying to prove above. If you look back above and in our statement, it's for any there exists. So universal existential type proof. And that's what we have here. I'm trying to prove that for all x, or any x if you would rather, there exists a y. It's the same type of problem, except this is easier because instead of an inequality, we have an equation. Okay, so can I prove this, and how do I prove it? Well, the trouble is you have to do an infinite number of things, right? And the way they usually describe it is kind of a game. So I'm sitting in my office, and a student walks in and is like, says, well, what about x equals 3? Okay, you're saying that for all x there exists a y, and here I am sitting in my office doing my work. And my student doesn't believe it, right? He's saying, well, what about x equals 3? So I go, okay, I could probably figure that out. I'm doing algebra. Y equals 4 is my solution, right? And so he's going, x equals 3, what about that? And I say, well, I thought about it, and y equals 4. So he comes in the next day, and he's like, well, what about if it's a negative number, right? Maybe that's different. You didn't think about that, did you, buddy? And then I get out my paper, and I say, okay, I'm going to put -2, and then plus y equals 7, and then y equals, add 2 to the most, oh, it's 9. Y equals 9, right? Okay, and then he comes back the next day. He's like, well, smarty pants, what about 0? 0 is a funny number. It's not positive. It's not negative. Maybe it won't work. Okay, so I get out my paper again and put in 0 there, right? 7. Oh, y equals 7. So it seems like there's existing, a y value for any x value that this kid brings into my office. And I'm sick of it by now, right? I got a lot of stuff to do. I'm grading papers all over the place. I'm like practically a tech person at this point. People are calling me about tech issues left and right. So I'm sick of it. So what I do is make a computer program. Okay, I can see the kid coming into my office. He's about to go blah, blah, blah. And so I just make a computer program. And when I do computer programming, it's archaic because I'm like old now. And we actually used tape machines when I was a kid to do computer programs. This is even before floppy disks, right? So it looks like a tape machine. Okay. and I program the thing to take whatever x value that this person gives me and plug it into this expression, right? Y equals 7 minus x. Right? So I don't have to be there. And right, so he says x equals 1, and the computer just plugs it in there and outputs 6. Okay, so what I did there was back engineer a formula that I'm kind of making a computer program such that if anybody comes into the office and questions this proof, the computer will automatically output a number. So for any input, there's always an output. And that's how you prove universal existential proofs. You build a machine such that for any input, there's an output. So what we essentially want to do with these proofs is build a machine such that for any input, so for any epsilon that you give me, so in the first example it's 0.01, in the second example 0.00, sorry, in the second example I guess it was, where are you? 0.001. For any epsilon that you give me, I can build you a delta, or I can build a machine that finds you a delta such that it'll always find something, okay? And that's what we're after. We're after this machine. That's what all the back engineering was about. And, you know, it's only difficult because there's all of these absolute values and inequalities. In this context, it's a lot easier, right? I found my y value for any given x. So basically, in these proofs, I need to find an epsilon value for any given delta. Okay. In these proofs, they usually just, I work them like fill in the blanks. So if you go online to the Cuyahoga Community College and you go into Blackboard, and you wait a half hour, then you go in the courses, and then you go into 1610, and then you go into course content. You'll see a delta epsilon fill in the blank. There's also there will be some on the test, okay, that you'll have to do as well. But let's look at my sort of worksheet. And these types of proofs are basically like fill in the blank proofs at this point. Some proofs you have to think a bit about, but ultimately these sort of just evolve into fill in the blanks. Okay, so I have a worksheet there for you that you could try to do these, and hopefully you get some practice. Okay, and there's mainly just these two types of proofs, the linear and the quadratic. In reality, there's probably about 13 different types of these delta epsilon proofs. If you get really into it, you go online and kind of classify them and put them in your sketchbook or whatever. Okay, so anyways, let's go at it, right? So we want to officially do an epsilon delta proof. Use epsilon delta to prove this limit, the limit as x goes to 2 of 3x minus 2 equals 4. Okay, so what are we doing? First off, we wish to find a delta, basically, such that for any epsilon, and these deltas have to be greater than 0, and the epsilon has to be greater than 0, such that for any epsilon greater than 0, if the distance between x and 2 is greater than 0 but less than delta, then the distance between f of x, which is 3x minus 2, and 4 is less than epsilon. Okay, so all of that information is coming straight from the limit, right? So the x minus 2 comes from that part, and then the 3x minus 2 comes from that part. And then the 4 comes from what the limit equals. Okay, so what we want to do first is back engineer the delta. Okay, so note, we begin with this 3x minus 2 minus 4 thing. What does that equal? That equals the 3x minus 6, and then we're trying to back engineer an expression with x minus 2 in it. So that will equal 3 times x minus 2, and then the product rule for absolute values, that's the same as the absolute value of 3 times the absolute value of x minus 2. The absolute value of 3 is just 3 times x minus 2, and then that's going to give us our delta. Okay, your delta is going to be epsilon all over this number that's in front. Okay, so this 3 kind of tells you the denominator of your delta. So it's going to tell us delta equals epsilon over 3. Okay. If you wanted to, you could literally take the 3 times the absolute value of x minus 2 and say that needs to be less than epsilon, and then solve for x minus 2, epsilon over 3. But you get the same answer, right? So it's just we need delta to be epsilon over 3. Okay, so once you find your delta, you need to show that the thing works. So that's the next sort of line. So suppose this thing is less than the delta we just found. So suppose x minus 2 is less than the delta, which will equal, in our case, epsilon over 3. And then we show it works. Note this f of x minus L, which we defined above to be 3x minus 2 minus 4, equals absolute value of 3x minus 6. I mean, we already sort of did this above, you know, it's a bit silly to do it again, but we do. 3 times x minus 2, and then we use the inequality to make our final statement. So this will be less than 3 times epsilon over 3, because x minus 2 is less than epsilon over 3. Okay, and then the 3's cancel, and then that shows that 3x minus 2 minus 4 is less than epsilon, which is what we were trying to show. Okay, okay, so online, let's look at my so we wish to find, it follows kind of the same order as what I just did. So in this case, 4x, if 4x plus 1 minus 9, no, sorry, if x minus 2 is 0, if x minus 2 is greater than 0 but less than delta, then absolute value of 4x plus 1 minus 9 is less than epsilon. And then I kind of had to do the scratch work in my head, right? So to find the delta, you have to kind of do the scratch work to the side. Let me do this example here that's on my worksheet. Say 4x plus 1. Okay, so did I just do the same thing? No. Okay, so the worksheet example, prove the limit of, let's see, 4x plus 1 as x goes to 2. So prove that this thing equals 9, right? And so the fill in the blanks, we wish to find a delta such that for any epsilon. And so we wish to find a delta greater than 0 such that for any epsilon greater than 0, if, and then I think we have some fill in the blank stuff, right? So yeah, if blank, then blank. So if, and I'm really strict about this because this is a strict definition, right? So if I need to show that 0 less than absolute values, and I need all my P's and Q's straight, then the absolute value of 4x plus 1 minus 9 is less than epsilon. Okay. Okay, so what do we have next? Suppose 0 is less than x minus 2 is less than delta, which equals. Okay, so suppose 0 is less than absolute value of x minus 2, which is less than delta, which equals blank. Okay, so this is where I have to do my back engineering. Above, I kind of did it right here, but in the proof you don't show this stuff because it's a bit silly, because you end up having to show it again right here, right? And in proofs you want to make it as streamlined and as clear as possible. So we kind of just do that to the side at this point. So in the upper right there in my margin, that's where I do my back engineering. Okay, so this thing equals 4x minus 8, and then I can factor out the 4, and I get x minus 2. This needs to be less than my epsilon, so I need to put x minus 2 less than epsilon over 4, right? So delta equals epsilon over 4 in that blank. And then I show it works. So note, okay, so note, the absolute value 4x plus 1 minus 9 is equal to the absolute value of 4x minus 8. Okay, let me move this thing. And then that equals 4 times x minus 2, I believe. So we need, another blank. What goes there? So that's 4 times the absolute value of x minus 2. And then that will be less than 4 times epsilon over 4, which will equal epsilon. So those are the other blanks, which is what we wanted to show. Okay. Okay, so that's the simple first intro to the proofs. Let's look at the other type of proof now. So prove something like the limit as x goes to 2 of x squared minus 1 is equal to 3. Okay, so this is a quadratic type proof, and for these you're going to have to do that extra part where we made a restriction, right? So it was this thing. We kind of said, okay, it doesn't matter what happens far away because we only care about the getting really close to 4. So we made this restriction that the distance between x and 4 is less than 1. Okay, and then I kind of screwed up and let the cat out of the bag. We're going to have to do a minimum function on the delta. Okay. So let's see how these things work. Okay, and I start out the same way. I want to show, right? We wish to find a delta. Let me get back into the white pen. We wish to find a delta greater than 0 such that if epsilon, we wish to find delta greater than 0 such that if the distance between x and 2 is less than this delta, then the distance between x squared, the f of x, and 3 is less than epsilon. Okay, so the back engineering part. So notice, we kind of begin with this x squared minus 1 minus 3 and try to back engineer this x minus 2. Okay, so this will be x squared minus 4, and then I can factor that, x minus 2, x plus 2, and then I could use the product rule for absolute values. This will be x minus 2, x plus 2, and I'm trying to find a delta. Right. The only problem is this x plus 2 thing. So what I do is make a restriction. So suppose then the x minus 2 is less than 1. Okay. And then I can get bound on the x plus 2 part. So x minus 2 less than 1 is x minus 2 less than 1 greater than negative 1. And then you could add 2 to all 3 sides. So that's greater than 2, less than 3, greater than 1. Okay, so then you could add 2. So x plus 2 is less than 5, greater than 3. And therefore, the absolute value of x plus 2 must be less than 5. Okay, so for my delta this time, I have this x minus 2 times x plus 2. I just showed that this is less than 5 times x minus 2 when I make x minus 2 less than 1. And I need to make that less than our epsilon, right? So you just, again, divide by the 5. And we have epsilon over 5, kind of. There's 2 parts to it, though. Okay, there's this and this. So for my delta, I have to use this min function. I need the min of 1 and epsilon over 5. Okay. Okay. So once I establish that, then I can show it works. So we're supposing then that this x minus 2 thing is less than this delta, which we've defined to be the minimum of 1 and epsilon over 5. Okay. Okay. Then I note the f of x minus L part is 2x minus 5. Sorry, I screw up. It's x squared minus 1 minus 3. Sorry. Then this x squared minus 1 minus 3 is equal to absolute value of x minus 4 times absolute value of x minus 2 times x plus 2 eventually, right? And then that'll be less than absolute value of x minus 2 times x plus absolute value of x plus 2. So absolute value of x plus 2 is less than 5. Okay, so I have, and then x minus 2 is less than epsilon over 5. So it'll be epsilon over 5 times 5, which is equal to epsilon, which is what I want. Okay, okay. So the hard part now is going back to the fill in the blank. And if you see the fill in the blank again, that back engineering part is left out of the actual proof. Okay, so I need to go and do a more formalized version where I'm filling in the blanks. And let's look at our thing online, and then we'll cut the video short. Yeah, that'll be the end of the video. Okay, so fill in the blanks to complete the proof, and I think I just did the same exact problem by coincidence. Oh, yeah, I did. Okay, so we'll make up a new one. Prove that the limit as x goes to 4 of x squared minus 9 is equal to 7, right? Or maybe even, let's use 3, okay? Because I think I just did that one above. 3. Humans are so predictable, right? 9 minus 9 equals 0. That'll be too weird. Let's go with 5. Okay. So 25 minus 9 is 16. Okay, so how does this type of proof go then? We wish to find a delta such that for any epsilon. Okay, so we wish to find a delta greater than 0 such that for any epsilon greater than 0, if the distance between x and 5 is less than delta, then the distance between x squared minus 9 and 16 is less than epsilon. Okay, so getting back to the proof, and then we suppose the delta. Okay, so suppose that 0 is less than x minus 5 is less than delta, which equals the min of something. Okay, and now we have to do our back engineering in our margin. So let me just put it to the side over here. So I need x squared minus 9 minus 16. That is x squared minus 25, which is x minus 5 times x plus 5. You need to make that first restriction that x minus 5 is less than 1. Okay, and then I'll have x minus 5 is in between 1 and negative 1, and then you can add 10 to all 3 sides, and you get x plus 5 less than 11 but greater than 9. So the x minus 5 times x plus 5 will be less than 11 times the absolute value of x minus 5. And so we want to make our epsilon, or delta rather, equal to epsilon over the 11. Okay? So we have epsilon over 11. And then we have to show it works, right? So note then, so note the absolute value of x squared minus 9 minus 16 is equal to the absolute value of x squared minus 25, which is equal to x minus 5 times x plus 5, which will be less than epsilon over 11. So the x minus 5 is less than the epsilon over 11 times x plus 5, which is less than 11, okay, from before. And of course that equals epsilon, which is what we wanted to show. Okay, so this stuff's really hard, but it's why is it important? It's because your mathematics, the distance in your mathematical universe may be different. If you have studied like quantum physics, the distances there are different. They use like some weird space, like a Knox space or a Hausdorff space or something like that. And in those universes, the distances are not intuitive like in our universe. Like I can visually see the distance between me and my computer. But in quantum physics, those distances are not the same. They don't have the same measurement to them. Okay, but you can still define this limit idea in that different universe by just replacing the absolute value distance stuff with some other distance formula, which may exist on the quantum level. You just have to figure out what that distance formula is. Okay, so if you have that established, you can redefine all of calculus to work in that new universe. Okay, just by doing some easy replacements, like back in the definition of the limit up here. If you just do some replacements on this statement and this statement with different distance formulas, so you would say maybe the distance between x and c, whatever that is, and then some other distance between f of x and L, you can make it general, and then the sky's the limit, you know. Okay, so that's why it's high-powered stuff, and if you keep taking math, you'll beat it to death. But let's call it a day, and I'll see you next time. Okay.